All right, we're going to talk about Huygens' principle. So with waves, we've looked at how waves kind of travel in lines. So if you think about sound waves or just mechanical waves in Unit 6, they just traveled in lines. And we looked at, how do waves travel in lines? And in our optics unit, light, we literally just modeled it like lines, like streams of particles. But light is an electromagnetic wave. It behaves like a wave as much as it does a particle. And in order to really start understanding waves, you have to understand Huygens' principle. Huygens' principle, it's kind of interesting. It says that, excuse me for my cough, a wavefront is formed by, okay, actually before I get into that, I guess I should explain what a wavefront is. So if you have like a speaker that's like emitting sound waves in all directions, or let's start with that. Let's just start with this speaker example here. Waves, right? The sound waves will have crests and troughs, and the wavefront represents some part of that phase, right? So, a wavefront, the line could represent a crest, right? So this is a crest, this is a crest, this is a crest, and that would mean if this distance is gonna equal one wavelength, right? The distance between each line would equal a wavelength. And you could also say the line represents a trough, right? If this was a trough and this was a trough and this was a trough, that's still that's still a wavelength between. So that's what I mean by it represents some part of the phase of that wave. It could represent, the equilibrium position, right? The line just represents some part of that phase. If you have, you could also have, right, a really big speaker, right? And that's just like pushing, instead of radiating sound everywhere, it just creates sound waves in one direction. And that, it would create wavefronts that look like this, where you just have crest to crest, right? Crest, 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 or trough, 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 whatever that line represents. You can kind of decide that, right? It just represents one, like a phase of that wave. Doesn't really matter specifically what phase, it just matters that, hey, the distance would always be a wavelength in between. So Huygens' principle tells us that the next wavefront that will be created after a certain amount of time, right? It will end up equaling, or not equaling, but if you imagine each point on this wavefront to be sources of these wavelets, right? If each point kind of is a source of a secondary wave, right? If you were to imagine this, and these waves formed would ideally, go at the same speed as the actual wave. But if you imagine each point creating its own wave with this that propagates at the same speed and all like in all directions, right? It's propagating circularly. The next wavefront will equal, or I guess at least like the direction of the wavefront, right? The wavefront, if you would equal like the connection points between all of these wavelets, and it's kind of hard to draw them perfectly, but you could see that all of these wavelets would end up kind of, I wouldn't say constructively interfering, but the envelope where they all kind of meet, it's going to be the line tangent to that, to all those circles. And that's the next wavefront. So if you think about, hey, for a circular thing, right, you can imagine each point will, create their own waves, right? And then the wavefront will just be the connection point between all of those kind of wavelets after a certain amount of time. So that's really Huygens' principle. That's kind of what Huygens' principle tells us. I don't know if actually that's what's going on, you know what I mean? I don't know if in reality each point is actually creating secondary waves, or if this is just like a made up way to kind of predict where waves form, right? Like maybe like what I'm saying is maybe they don't actually produce waves, and this is just a method for finding the next wavefront by treating each point as a source of secondary waves, and by experiments we can kind of confirm that yes, this method works, right? I don't know if waves are actually being created or not, but it's still a really useful method for analyzing waves because it explains why do waves bend when they reach mediums, right? Or reach it or pass through different mediums. If this marker's getting kind of dead, if we had like a wave, right? A wavefront that is kind of entering a new medium, we know after one period really, the wave would be like right here and then right here, right? So if this is index of refraction, let's say n equals 1, and let's say this is n equals like 2 or whatever, this medium is slower. You know, we can use Huygens' principle and be like, okay, after 1 second, we get like a wave like this, right? Like if you think about all the wavelets formed by each point, you know, by our, you know, Huygens principle, right? Once the wave hits, so if this is the wave at this point, right? Once the wave hits here, and we can even what would happen is, well, let's even extend this wave till here, right? By the time the wave has hit this point. So what happens is, well, this wave, right? They still make their wavelets, but, and I'm drawing this really, really badly, I guess it would be more like this, right? But what ends up happening is here, the waves propagate slower. So the wavelet formed, if this is the distance, like the wave grows by the time, after a certain amount of time, t, right? Then that distance would be smaller here because for this wavelet right here, it's propagating at a slower speed. It's in the same amount of time, it's not going to have traveled as much distance. It's not going to have grown as much. So when you do, and then it gets kind of funky here because it's like, well, then this wave point's kind of like here. But the main idea, the main gist is that, yeah, it's going to bend when you start connecting those lines, right? When you connect this circle to these circles, it looks like it has bends. And if you continue that, right, if this wave continues, then this source right here, right, it still makes waves, right? I'm really bad at drawing the wavelets, but the idea is if you can imagine the wavelets, they're going to be they're going to have bent towards the normal. It looks like the wavefront has bent away from the normal, but now the whole wave front itself is traveling, instead of this angle, it's traveling at this angle, right? Like it's traveling like this instead of like this. So you could see the direction of travel for the wave is bent towards the normal. So that's an example of how Huygens' principle is applied to kind of understand, like, hey, why do waves bend when they reach different mediums? So that's Huygens' principle. Just a little bit of an explanation there, so that we can, excuse me, good Lord, so that we could understand diffraction. Thank you for watching.